looking at data first. Then I told you the principle of finding the line. And I also told you the statistical thinking, or at least the what lies behind to put this into a statistical reasoning framework doing this exercise. It's easy to go in Excel and put a line in your data. You probably, as I said, you've done that maybe 100 times in your life already. But did you think about what comes now when you did it? Did you think about the core question that carries the whole idea of this course again and again and again and again? Whenever I compute something, for instance a line, which is given by a slope and an intercept, I should ask myself, how good is this line for me? How good is this line for whatever purpose I'm going to use this line for? I mean, when I get adult and I get a job, I don't run around making lines for the fun of it. I make lines because it's business or science. So there is a purpose with this line. So it has a meaning. It's not, we need to think about, can I use this line? And if I use it, what's the risk in using it? What's the error I make if I go ahead and use it? So if I redid it, and that's the core thinking, we should try to answer this question. And this is a repeat, and I'm going to repeat a few times before the end of this course. The way we should think is, what if I did it again? Would I get a different number? Yes, of course. We would have even realized in 3rd grade already. Of course, if I redo this experiment in another classroom, if I have a classroom experiment, will I get the same result? No, of course I won't. I mean, no one would expect to get exactly the same result. So we're all pretty well equipped with this level of intelligence to realize that we have a challenge here. The question is, can we deal with this challenge in a specific way? And that's what you're learning in this course. To think like this and have the tools to make that operational. Those concerns that we should have, all of us, all the time when we see numbers. You know the answer to this question. Of course, they are random variables. If you take a new sample, they will have a new value. That's how it is. That's the kind of the name of the game here. So we should be a little more specific and ask the question, what is really the sampling distribution of such estimators? How will intercepts and slopes change from sample to sample? If I know that, if I can answer that question, I am maximal intelligent. I can deal with it because I know what the variability is, right? So we should see if we could find out about that. And even though this is, let's try this now. I think we have the time to actually do it. Before I show you the results, given the idea that I taught you last time with simulations and all, you could in fact yourself investigate this question. I didn't teach you to do simulations in linear regression settings, but I did tell you that the idea of simulation is a generic one that can be used anywhere. So with a little bit of adding 2 and 2 to get 5, or using competences from 2 different places at the same time, you would be able to actually do the following. And if you weren't able, you could download my R code and redo it. Let's try. Here is, you know, I share all the R code with you. Let's try it. This is what I showed before, so let's not go there. But now this is what I showed before. Here we are. Here the heading is, see how the parameter estimates are distributed. What I'll do now to investigate this, so this is a toy exam. Now I'll show you some simulation for the fun of it, or rather for the learning purpose of it. Not because I expect you to be able to do simulations in linear regression. Well, I expect that some of you are intelligent enough to be able to do it, but I'm not going to test it in this course, whether you can do it. But I'm going to share this little event with you to make you learn. What I'm doing is that 1,000 times, and here's a for loop, so for 1 it's a very naively implemented routine here. I make a simple for loop, and each time I generate some new data. So I do a new experiment. So I do a N20 experiment. I try to do that 1,000 times. And then let me see what happens with such 1,000 repeatedly computed slopes and intercepts. How do they behave? Now this is a toy example, so I control the truth here. The truth is an intercept of 50 and a slope of 200. And the noise, the sigma, the error is on average 90. Standard deviation 90. So I simulate the data. That's what I do in this line, right? R norm for the error. So I simulate the error and I add in the line. Then each time I make a regression and I extract the intercept and the slope. And at the end of it, I'm looking at the intercept and the slope. There's 1,000 intercept and 1,000 slopes, right? A little simulation example to make us think about the question I asked. What the heck will happen to such intercept and slopes in a case where I have sampled only 20 persons in these experiments? So pretty small data compared to the life of big data age we've been hitting here. So it's, you wouldn't ever admit at a big data conference that you ever looked at small data like this, but here they are. Beta 0 hat, beta 1 hat. Well, the truth, let's talk about the slope. The true slope was 200, right? It appears that my computation machine here, the least squares method, that produces sample slopes to me, that behaves pretty reasonable, right? On the average, it seems like it hit the truth 200. That's a good property for an estimator, that it hits the truth on average. It's unbiased, actually. What about the variability? That's the core question, actually. Then how certain would such a slope estimate be? Well, plus minus 20, roughly, right? Plus minus, well, it's plus minus 40. If I look at this, 200, 240, 160, that corresponds to a standard deviation of roughly 20, right? Because it's like plus minus 2 standard deviations on each side. So probably the sampling error is around 20 for such an experiment like this. Well, we could just do such simulations each time if we wanted. We could do bootstrapping, either parametric, as I do here, or non-parametric if we wanted. When we have real data, that's a perfectly valid approach that some would use. However, let me, before we break it, give you the theoretical results that can be nicely extracted to put those variabilities that I just showed you into a formula, because such a formula exists. If you assume the normality thing, if you believe that your phenomenon is a normal thing, that the residuals are normally distributed, that's an assumption. It's not always true. It's an assumption. Or maybe if you have large samples, it might not be too bad still to assume. Let's just forget about this cousin here. If the mean is 0, that's 0 also, so that's not going to ruin anything for us. The most important part are these two, and the most important among the most important one is this one. Here it states that the variance of the estimation of beta 1, that is the slope, that's the original variance divided by this squared sum of x deviances. Let me just check. Yeah. Can you recognize this formula? Maybe not exactly like that, but I hope we can recognize that it at least resembles something. Please remember that when we looked at the variance of a mean, the variance of a mean was sigma squared divided by n. That was leading us to the sampling error of the sample mean, Now actually, this is more or less a formula like that, but we have some of the X data in there. But the thing is that this I want to just check what I brought here. Yes, let's look at it here. Let me see, how should I put the words? Actually, these two formulas are reproduced here, just to make it even more explicit what these two formulas are doing for us. There's a bit of hat here, but it's the same formulas. And if we focus on the one that I was looking at here, it's instead like this. This is the standard error, the sampling uncertainty of the slope. This is the number that quantifies how certain the slope is estimated, or maybe I should say uncertain. And here we see that this is what we called SXX. This is SXX. So it's just a name for the sum of all these squares. So it's a bit like a sum of ones that would become n, like that. So it resembles the n from before, actually. And the sigma, that's important also, to actually use these formulas. Like when we did statistics for a mean, we need an estimate of the sigma. And in this case, our estimate of the sigma is to take all these residuals, deviances, errors, square them, add them up, and then average them. But we average them not by n, not by n minus 1, as we've done a lot previously, but now we do it by n minus 2. But intuitively, interpretational, it's still the average, so sort of. So this is the average deviation, I should say square deviation from the line. And now we can do statistics for intercept and slope. But we'll do that when we have braked. And let's do one little thing. Good. In spite of the right-left confusion and whatever, we managed to hit the right one. Of course, that was the largest one. One more thing before the break. The question should appear familiar now. Got you there, tricked you. This is a classical example of visual, what's it called? That it's very difficult to interpret vertical distances on a very steep line like that. You can go check if you want. They're exactly on average the same in the two plots. They just appear much larger like this, but it's very difficult to see it like that because the line you don't see the vertical difference when you get like that. So that's actually the point. So we have another one on the top. Good job there. Let's break it and be back here in 15 minutes, 3 after on this one.